Hello, welcome to another module in this massive open online course. In this module, let us start looking at another very important component or another very important topic in linear algebra, and that is matrices. So far we have looked at vectors. Now let us start looking also at matrices. All right. So obviously when we talk about linear algebra, it is essentially a lot of discussion about matrices. Sometimes linear algebra is also known as matrix algebra for the same reason. Alright, so you have an M cross N matrix is simply an M cross N array of scalars. Of course, if n equal to 1, then it becomes a vector. But for a general M cross N array, it becomes a matrix, right. So you have A equals A11, A12, A13, so on up to A1n. Then you have the second row A22, A23, A2 and so on, and then you have the mth row AM1, AM2, so on, AMN, and therefore this is an M cross N matrix in the sense that this has M column, M rows, right. You can see this has M rows and this has n columns, right, and you can essentially look at each column also as a vector, which is going to be very helpful. So we can call this as A1 bar, A2 bar, and then you have AN bar. So you can think of this as putting together of n columns of or n vectors of m elements is. So you can also think of this as A1 bar, A2 bar, AN bar. These are the columns, or these are n vectors of size m cross 1. Okay. So M is the number of rows, N is the number of columns, and Aij, if you look at this entry A23, for instance, A23 is the entry in second row and third column, right. So A23, for example, A23 equals the entry or in second row and third column, right, and Aij in general equals the entry or coefficient, whatever you call it, entry or element of the matrix, depending on element in ith row and jth column. So you have Aij 1 less than or equal to I less than or equal to m, 1 less than or equal to j less than or equal to, that is column index, row index. This is basically your row index, and this is basically your column index. Okay, so this is essentially your matrix. This is an M cross N matrix, right. Let us take a simple example. Again, there are many examples. I mean, most of you might have already encountered this many times. So let us take a simple example: 3 minus 1 2 minus 2 4. So this is naturally, this has 2 rows and this has 3 columns. So, this is a 2 cross 3 matrix, right. And if you look at the entry A22, that is second row second column, this is equal to 4 and so on, and then A23 equals second row third column, that entry is 3 and so on and so forth, right. So, it is a very, and another way of representing this is you can also represent this Aijth entry is Aij. So, this is another way of representing ijth entry, another way of representing the ijth entry of the matrix A. Also equally apparent, if AMN is real, that is all elements are real, A is real matrix. If AMN is complex, then A is in fact, the way to represent this is, we will say A belongs to the set of M cross N real matrices, right. So, this is essentially the set of and we say here A belongs to the complex M cross N. So, this is essentially set of M cross N set of M cross N complex matrices, right. So, this is, you have the set of M cross N real matrices and you have the set of M cross N complex matrices. Okay. Let us look at some basic operations. Again, many of you might already be familiar with this. Basic operations. For instance, for example, let us look at matrix addition. What do we mean by matrix addition? A plus B. When can you add two matrices? So, we can add two matrices A and B, right. So, we can add matrix, we can add two matrices A and B only if they have same size or essentially same dimension, that is A is M cross N and B is also. So, matrix addition is only defined when both the matrices are of the same size, otherwise you cannot add the matrices, and the addition is simple, you add them element wise, right. So, you add the 1 comma 1 element of A, 1 comma 1 element of B, that gives you the 1 comma 1 element of the addition, right. So, the way to represent this is C equal to A plus B. C will also be M cross N, and you can simply say each element C I j equals ijth element of A plus ijth element of B, or you can also write this, sometimes you will also see C I j equals Aij plus Bij. I mean all of these are, depending on how you define the notation, the context, I mean all of these are valid. I mean as long as it's clear what you're talking about, all of these are valid. And you can also write this as Cij equals Aij plus Bij and so on. Okay. Let us take a simple example. We have our matrix A, which is essentially 3 minus 1 2 minus 2 4 3 plus another matrix B, which is let us say 4 minus 3 6 2 2 minus 1. So, this is your A, this is your matrix B. So, 3 minus 1 2 minus 2 4 3 4 minus 3 6 2 2 minus 1. So, both of these are essentially, you can see these are both 2 cross 3 matrices. So, you have C, which will be equal to, you add them element wise. So, you have this element adding with this element. So, 3 plus 4, that is 7. You have this element adding with this element, 2 plus 6, that will be the 1 cross 3 element, that is 8, and the 1 cross 2 element, that will be minus 4, so 0 6. So, you are simply adding them element wise, alright. So, that is essentially what you have, and this is essentially your matrix C. So, you are essentially adding the elements of A, you are adding essentially element wise, alright, each element of A with corresponding element of B, and you get the matrix C, which is of the same size as A and B. Okay. Scalar multiplication, again very simple. So, you have the concept of scalar multiplication. That is similar to vectors. Once again, if you multiply a matrix A by a scalar, essentially it means that if you look at its ijth element, right, that is simply k times A ij, that is take each element of matrix multiplied by the scalar, right. So, what it is doing is essentially, what this is doing is multiply each element of A by the scalar. Let us take a simple example, 2 times A, that is twice 3 minus 1 2 minus 2 4 3. You take, this is our matrix A, this is our matrix A. So, that will be, you multiply each element. So, that will be 2 times 3 6 minus 2 4 minus 4 8 6. So, you take each element of A multiplied by that scalar quantity, which in this case is 2. So, that is the property of scalar multiplication of matrices. So, this is essentially the property of Let us now consider matrix multiplication. How and when can you multiply two matrices? So, this is and let us consider again two matrices AB. A is M cross N and B is P cross Q. Now you can multiply A and B only if this n is equal to P. So AB or A times B is defined only if or only when, or let us say only if n equal to P, that is number of columns of first matrix should be equal to the, so that is number of columns of A should be equal to number of columns of B, alright. So that is important, number of columns of A equal to number of rows of B. Is equal to number of rows of B. Number of columns of A should be equal to number of rows of B, and we have A and B. So we have, now we have A and B. A is, let us say, as we said, A is M cross N, B is N cross Q. So number of columns of A is equal to number of rows of B, which is N. Then the product C equal to AB is defined as follows, that is for L equal to, that is if you look at the ijth element of C, so that is L equal to 1 to N AIL times BLJ, alright. So essentially what you can say is the Cij, the way to look at this is the inner product of ith row of A with jth column of B. So this is the inner product of ith row of A with inner product of ith row of A with the jth column of B. Let us take a simple example to look at this. Let us take an example. For instance, let us say we have A equals the matrix, that is your 1 2 3 4 5 6, and B equals the matrix minus 1 1, sorry, 1 minus 1 1 minus 2 1 3. These are two matrices, right. So we have A equal to 1 2 3 4 5 6, B equals minus 1 1 minus 1 1 minus 2 1 3, and now and of course you can see A is 2 cross 3 and B is 3 cross 2. So number of rows of A equals number of columns B. So A into B is defined, right, because you have number of columns of A equal to number of rows of B, okay. And then now let us look at how to compute A times B. So this will be equal to, A times B will be equal to so essentially we take, so for the 1 comma 1 element we take the inner product of the first row of A with the first column of B. So you put these two together, inner product of these two, that gives the 1 comma 1 element. So the 1 comma 1 element would be, that would be 1 into 1 plus 2 into minus 1, that is minus 1 plus 3. So that would be equal to 2. Now, the 1 comma 2 element would be first row of A and the second column. So, this and this, first row of A, second column of B, this gives you the 1 comma 2 element. So, that would be minus 2 plus 2, this is 0, 3 into 3, 9. Now, second row of A, first column of B, that gives you the 2 comma 1 element. So, this gives you the 2 comma element, that is 4 minus 5, that is minus 1 plus 6. So, that is 5, and finally, second row of A, second column of B, this gives the 2 comma 2 element, that is minus 8 plus 5, that is minus 3 plus 18, that is 15. So, this is, so A is m cross n, B is n cross q, A into B is of size m cross q, right. So, A in this example, A is 2 cross 3, B is 3 cross 2, this implies AB is of size 2 cross 2, that is what we are saying. So, this is essentially your A into B, alright. So, this is essentially your matrix A into B, and as we have seen, each ijth element of AB is inner product of ith row of A, inner product of ith row of A and the jth column of B, alright. So, we will stop. So, with this aspect, we have looked at the basics of matrices, introduction, properties of the matrices, addition, scalar multiplication, multiplication of matrices, and so on. So, let us stop this module here and we will continue in the next module. Thank you very much.